Okay, well, very good. So what we've just done was to look at Schrodinger's equation for the case of a one-dimensional confining potential and show that an electron moving in this potential has two parts to its motion. It's confined in the direction perpendicular to the plane, and that part of its wave function obeys an equation that looks like the one-dimensional Schrodinger equation. On the other hand, the particle is free to move in the plane of motion, in the plane of the quantum well, and that gives a different type of behavior. Here, let's take a look where we are and see what this implies about the energy levels for such a system. Very good. So taking up our story then, what we found is that the electrons are free to move in the plane. And like free particles, they have a component to their energy, E parallel, which is just their kinetic energy in the plane. On the other hand, the electrons are confined perpendicular to the plane. And what we found is that the part of their wave function that describes how the wave function varies in the z direction, z of z, we called it, that this obeys something that looks like Schrodinger's equation for a one-dimensional problem. Okay? And this specifies the part of the energy associated with this confining potential. We called it E perpendicular. And of course, the total energy will be the sum of these. Okay? So here, let's take a look at an example. Let's suppose that we have a one-dimensional confining potential such that the potential energy in the z direction is just our old standby, the infinite well potential. Okay? That is a graph of v of z as a function of position. Looks like this. So we're imagining that our that our layer has a thickness L, and that the electron is strictly confined to that layer. Okay? But of course, the particles are free to move in the x and y direction. So for this confining potential, the nice thing is, the reason that we picked this is that it's such a simple problem that we already know the answers. Then we know the perpendicular energies. They're just given by this expression, h bar squared pi squared over 2m star L squared times n squared, where n is a quantum number. Okay? And we even know the wave function in the z of z. It's just given by root 2 over L times sine n pi over L times z. We know these because we remember them from modern physics. Or again, it's such a simple problem, we can work it out on one side of one sheet of paper. So the perpendicular energy and the perpendicular part of the wave function look exactly like they do for a one-dimensional particle in a box. Okay? So this part of the problem is very easy. The second part of the problem is easy too. The particles are simply free to move in the x and y direction. And that means that the energies, E parallel, are just given by h bar squared K parallel squared over 2m star. Okay. And the wave function that describes this part of the motion is just equal to some constant times e to the I K parallel dot R parallel. Okay? Very good. And then the total energy is the sum of these two. And maybe it's easiest to describe these energies with a sketch. There we are. My sketch will have two parts here, okay? The first part just shows the energies E perpendicular. So I have the energy of the first state, okay, I'll just draw the third one here. Okay. And then we have to include now when we look at the total energy, both the energy associated with the confinement here and the kinetic energy in plane. What that means is that we're going to have not single states, but subbands of states. Well, this is going to be a little hard for me to draw. There we go. And give me a second, I can finish my drawing. Actually, I'm just going to pause while I do that. Okay, there we are. So now look, what we end up with are bands of states, or these are called subbands. There's one band of states associated with each confined state from the confinement in the perpendicular direction. So this one is the band associated with n equals 1, n equals 2, n equals 3, and so on. And in each case, the energy is equal to the energy of the confined state plus the kinetic energy due to the in-plane motion. So for the energy levels of electrons in a parabolic well, you get subbands of subbands of states, okay? So that took a little explaining. We went through a long explanation to get to this, but that's the important point. We don't get discrete energy levels, we get subbands of states separated in this way. Okay, well now let's look at one more thing. Suppose that we're looking at energy levels in a semiconductor quantum well. And so let's suppose that this has grown the way many of these are, where we've grown a wide bandgap semiconductor, maybe aluminum arsenide or aluminum gallium arsenide. And on top of that, we've grown a thin layer of a smaller bandgap semiconductor before we went back to the larger bandgap semiconductor. And in this way, we've made a confining potential for electrons for a quantum well. Okay. According to what we've learned so far, we can find the energy levels of this system by first considering this one-dimensional potential. We have a one-dimensional potential for electrons here, and a one-dimensional potential for holes here. And each of these looks like a finite well potential in this simple case. The finite well, you'll remember, is a problem that we solved back in modern physics. And if you've taken quantum mechanics, you've seen it again, no doubt. And you can imagine that we would find some energy levels. Perhaps this is one. And this is the second one. Those would be the confined electron states. And then we might find some confined hole states as well. I'll just sketch in a couple to give us the idea. Oh gosh, that one didn't work out. I shouldn't be so particular, right? We're just making a sketch. Ah, okay. You get the idea. So what kind of energy levels does this create? Well, from what we've learned so far, what we expect is to find electron energy subbands. Like this. There we are. Oh. Oh my gosh. I think I'm paying heavily for my desire to make this look simple. Okay, there are my two electron energy subbands in the conduction band, but we'll also have hole subbands in the valence band. And I'll try to draw those. There's the first of these. Hold on one second. Okay, very good. So when we're done, we have electron subbands. And then we have hole subbands. These have different curvature because the electrons in the holes have different effective masses. Okay? And something else to notice is that the separation between the minimum energy of the electron subbands and the hole subbands, maximum energy of the hole subbands, is generally larger than the band gap due to the confinement energy in each of the bands due to the confining potential. Okay? All right. I think we'll stop here and then we'll talk about transitions between these states in the next video. But I think we've spent long enough, so I think I'm going to hold off on the next video until tomorrow. All right. Bye-bye. See you in class.